Hello? Hello?
Hello.
How's it going?
Good.
So I'm not sure if anyone else is coming tonight.
Oh,
I'm sorry?
Okay. I watched the video
You were saying? Okay, good.
and yeah, I have a few
And then so I
questions.
think it might just be the two of us tonight. So yeah, so I have a feeling it might just be the two of us tonight. And so let me open up the video, the file, and then we can just talk about this.
Okay.
Okay. Okay. You should be able to see the screen now.
Yes.
Okay. So one of the things that is, a real challenge with all this is everybody's on a different schedule, and it's tough to find times that work for everybody. So sometimes I think it's going to work better to have the lecture, whoever's able to watch it live, watches it live, and then we'll just have follow-up sessions. Okay, so would you tell me which material was good, which material do you have questions on, which material seems interesting?
I think I'm good with the first part.
Okay, that was the monovariants,
Yeah.
the tic-tac-toe, and then the rectangle game?
No, actually, I have question for Tic-Tac-Toe.
Okay. So, which part of tic-tac-toe? Tell me when to stop.
Here, yeah.
Okay. So what is your question?
I don't get it. Like, I don't understand the rule.
Okay, so let me go back and explain what goes on. So right now the board is empty, and there are two players, play one and play two, and we'll assume they each start with $1,000. And the way it works is for each move, each person makes a secret bid, some amount of money. And then whoever bids most gets the move. And they give the other player. So at the end of the day, you don't care how much money you have. You only care about, did you get 3 in a row? Okay?
Okay.
So what it says over here is, imagine that player 1 bid $300 and player 2 bid $700. So player 2 bid more, so player 2 wins the bid. So they put an over under. Okay?
Yeah.
How much money do they have now?
The player 1 has 1,700.
Correct. And then player 2 has 300. And so let's say on the next bid, player 1 bid $99 and player 2 bid $100. So player 2 has gotten the first 2 moves. But notice that player 2 is now going to have only $200.
Yeah.
And so now, because they only have $200, player 1 can win the next bid by bidding $201. Player 1 can win the next bid by then bidding $402, and they can win the next bid by bidding $804. So even though it looked like player 2 was doing really well, player 2 had 2 in a row, and player 1 had nothing on the board, player 1 was then able to win the next 3 moves.
Okay.
So the point of this is that it's not always clear what the strategy should be. All things being equal, would you rather go first or second in tic-tac-toe?
Go first.
Yeah, and what square would you like to take?
Huh?
Which spot on the board would you like to take when you go first?
In the middle.
In the middle. So it's clear that you want to go first and you want to play in the middle. The question is, how much is that worth? And so here, it turns out player 2 bid far too much for the first move or for the first 2 moves. And by bidding so much, player 1 was then able to win the game. So the question becomes, what is the right strategy? How much should you bid to go first? Or, if we can't figure that out, an easier question is, how much is too much? If we bid so much for the first move that player 1 can then get the next 3 moves, we're in trouble. Or if we bid so much for the first 2 moves that player 1 can then get the next 3 moves, we're in trouble. So the goal is to try to figure out how much is too much. Now, this game has been analyzed. One of my friends actually was the one who analyzed this. So on the next page, we start looking, clearly if you bid $1,000, that's too much for the first move because now you have no money left.
1,000.
I'm sorry?
1,000.
Right. So we agree that if you each start off with $1,000, $1,000 is far too much to bid for the first move. We can do better. So just to make the analysis a little bit easier, we'll assume that if there's a tie, player 1 gets to move. Otherwise, you have to adjust all the bids by $1 or $2. That just makes the analysis a little bit uglier. So just to keep things simple, we'll assume that if there's a tie, player 1 gets the move. Okay?
Okay.
So let's say player 2 bids X dollars and wins. So then they go to having 1,000 minus X dollars, and player 1 goes to having 1,000 plus X dollars. And we want to see how much is too much to bid. Well, one simple solution is if player 1 can get the next 3 moves, then player 2 bid too much. Right?
Yeah.
So we want to figure out what value of X is so large that 1,000 plus X is enough to get the next 3 bids. So if we start looking at it, well, if player 1 gets the next 3 bids, then they have to be able to win no matter what player 2 bids. So the maximum player 2 could bid is 1,000 minus X.
Yeah.
So we'll have to assume then that player 1 bids 1,000 plus X and just barely wins. So that's why we're going to assume a tie now. Otherwise, they would have to bid $1 more than that. So player 1 now bids 1,000 minus X and just barely wins. So they go to 2X dollars, and player 2 has 2,000 minus 2X. And notice that everything still sums to 2,000. Now player 1 bids 2,000 minus 2X and just barely wins. That's the second move in a row. Player 2 goes to 4,000 minus 4X. Player 1 now bids 4,000 minus 4X and just barely wins. And so they have 8X minus 6,000 is how much they end up with. And player 2 has 8,000 minus 8X. So we need 4X minus 2,000, which was our last bid, to be greater than 4,000 minus 4X. Or when the dust settles, X has to be greater than or equal to 750. So if you bid, let's do it explicitly. If you bid $750 as player 2, then you get the move, but you go down to 250, and player one is at 1750. If you then bid your maximum available 250, and player one bids 250, player one will just barely win, and you both go down. You go down to 500, so you go up to 500, and player one goes down to 1500. You now bet $500. Player one can exactly tie you with $500. So now you both have $1,000. And we're assuming player one wins a tie. So now player one gets the last move. If you wanted player one not to win a tie, you would have to subtract just a little bit from 750, maybe subtract $8. And as a nice exercise, you could figure out just what you need to do. So the goal of this part of the lecture is to just introduce you to some of the issues and some of the challenges of trying to come up with strategies for games. And the goal is.
What if like they get same amount of bids?
What if they get the same amount of
Bids.
What if they have the same amount of money on a bid? Can you repeat the question? I wasn't able to hear you.
Like, what if like they bid same amount of money?
Okay, well, what I said is, in general, if they bid the same amount of money, you should have to rebid. But to make the analysis simpler, just say if they bid the same amount of money, player one wins. Otherwise, what we'd have to do is, instead of bidding $250, player one would have to bid $251 to win.
Yeah.
And that's going to make the analysis just a little bit uglier. Okay?
Okay.
So you could go through and you could figure out if they have to rebid on a tie, what would you do? And then you would need them to bet maybe a little bit more than $750 in order for player one to guarantee that they can get the next three turns.
Okay.
Okay. So again, the whole point of this is to just give you some sense of how we do strategies, how we analyze games. And sometimes the analysis is very complicated. And when it's very complicated, we can't maybe analyze the whole game, but maybe we can analyze part of the game and get some sense. And what we saw here is it's not a good idea to spend too much for the first move. Well, the first move is desirable.
Mm-hmm.
If you spend too much on it, you then put yourself in a terrible position for the rest of the game.
Okay.
So that's all I wanted you to get out of this.
Okay.
Okay. How is the stuff on the rectangle game?
I think I'm good with it.
Okay. How is the stuff on the zombie game?
Yeah, I haven't finished the whole video yet, so.
Okay.
What's the zombie games again?
So the zombie game, let me see if I can just jump to that slide. So if you share two walls with an infected cell, you become infected.
Oh, yeah.
And once infected, you are always infected. So if you look at this, do you see how there are three cells that are infected?
Yeah.
Which cells, which uninfected cells will become infected because they share at least two walls with infected cells? Anything in the first row.
This. Wait. The second one in the first row.
Excellent. Anything in the second row?
The third one.
Good. Anything in the fourth row? I'm sorry. Anything in the third?
No.
and nothing in the fourth row. So you're correct. Those two cells become infected. Now, in the next moment, does anything else in the first row get infected?
No.
What about the second row?
The last one.
Last one. Oh.
And the third one in the third row.
Excellent. And now, does anything in the first row become infected?
The last one.
Yep. And so at this point, the infection stabilizes and no new cells will be infected. Okay?
Okay.
So now the question is, here is, say, the board. What I want you to do is give me the easiest solution you can think of that guarantees that at some point in time, every cell on the board is infected. So you get to choose who was initially infected. How would you do that to guarantee that at some point later in time, everybody's infected? What's the best way to do it?
Make a checkboard.
There's something even simpler than that. For the checkerboard, you then have to argue that every cell that's not infected shares two neighbors. There's something even simpler than the checkerboard. What's the simplest configuration that ensures that everybody is eventually infected? The checkerboard is good, but there's something that's even simpler. For the checkerboard, you have to argue that the cells that aren't initially infected share walls and will become infected. There's something even simpler where you don't have to do that argument.
Like the whole board.
Yeah, the whole board. So one of the things I want you to learn, through our lectures is how to look at extreme cases.
Oh.
We're just trying to prove something. Look at the simplest case possible. So if we look at the case when everybody starts off infected, is it hard to prove that at some point in time everybody's infected?
Yeah.
Yeah, it's trivial. Now the next thing is, as you said, we could do the checkerboard.
Yeah.
And it's 50% better. You only need half as many cells. But initially, we infected everybody. That was n squared cells. Now we infect half of the board. That's 1/2 n squared. It's much less. It's 50%, but it's still infecting on the order of n squared. Can you do better? Can you give me a smaller number of cells that will guarantee that everybody becomes infected eventually? So we did infect everybody, then we infected the checkerboard. Can you give me something smaller that will eventually have everybody infected? Smaller than the checkerboard.
Like, one less.
So you could do one less.
Yeah.
But you could do a much, much, much smaller number. Can you think of any pattern that might be significantly smaller than the checkerboard? If you don't have any thoughts, that's fine, and I'll show you the solution. But can you think of any ideas? And normally what I would do is I would have you look at maybe a 2x2 board. Can you come up with a pattern on a 2x2 board that will guarantee everybody gets infected?
We just need to, like, in the We just need 2 on the corner.
Okay. And then what about on a 3 by 3?
In diagonal line?
Ah! And so what if we just infect the main diagonal? Well, on the next round, you're going to infect everybody above and below. Do you agree with that?
Yeah.
And in the next round, you infect everybody above and below, above and below, above and below. And you can see the infection spread. Oops. Okay?
Yeah.
So instead of having to infect on the order of n squared, we only have to infect on the order of n. That's much better.
Yeah.
The question becomes, is it possible to do it with just n minus 1? And the answer is no. And the solution uses something that's called a monovariant. And this is going to be a key object in our understanding the Fibonacci game later. So what we're going to do is we're going to look at the perimeter of the infection. Okay?
Okay.
It looks at the walls of all the infected cells that are external. So imagine we have a configuration like this where we have some cell that's about to become infected, and it has 2 neighbors that are infected and 2 neighbors that are not infected. Okay?
Okay.
When you look at what happens to the perimeter of the infection, these 2 walls here on this side and this side were originally part of the infection, and now they're gone because they now become internal walls. But these 2 walls here initially weren't part and now are. So there's no net change in the perimeter in this case of the infection. In this case, there's also no net change in the perimeter. But in this case, there is. We had 3 external walls. They all become internal walls, and then 1 wall that wasn't there before becomes a wall. So we gained 1 wall and lost 3. So the net change was we lost 2 walls. So do you agree that the perimeter of the infection goes down by 2 when we have 3 cells infected?
I don't get it.
Okay. So were you comfortable with the 2 case when 2 cells were infected? That the perimeter was unchanged?
Yes.
Okay. On this one, if you look, can you see my mouse when it moves?
Yeah.
So this is an external wall. 1, 2, 3. So you see how these 3 walls were all external walls and part of the perimeter. Once this cell becomes infected, they're now internal walls, and they don't count towards the perimeter of the infection.
Oh, yeah.
It does now, because we are assuming that this cell is not infected. So in this case, we lost 3 walls and gained 1, so the net change was a loss of 2. And then if we're in the situation where 4 neighbors were infected, then the perimeter goes down by 4. Okay?
Right.
So a monovariant is a quantity that can only move in one direction. So people's age is a monovariant. You can't get younger. People's weight, however, is not. You start gaining weight as you get small and getting older, but then you might become a little bit too heavy, so you might diet so you can lose weight. Or you can look at temperature. Most quantities in life are not moving just in one direction. When you find something that moves in just one direction, you can often use that to great benefit. And so now we know the perimeter can never increase as the infection spreads. So if n-1 cells are infected, the maximum possible perimeter would be if no wall was being shared by 2 infected cells. So do you agree that the maximum perimeter is 4 times n-1? Because each square has a perimeter of 4.
Isn't the maximum perimeter is 4 times 4?
Well, no, but I'm saying if only n-1 cells are infected, the maximum perimeter of the infection is 4 times n minus 1. We have n minus 1 cells that are infected.
Right.
So do you agree that the maximum infected perimeter is 4n minus 4?
Yeah.
But as you just remarked beautifully a moment ago, the perimeter of the whole thing is 4n. And so since the perimeter is 4n, if everything was infected, then the perimeter of the infection would have to be 4n. We know the perimeter is at most 4n minus 1. Oops. So there must be something that is safe. And what's wonderful about this is we don't have to look at different configurations. We don't have to go through all possible cases of how we might have something infected. We showed that the perimeter of the infection can never increase. And so given that we start off at most at 4n minus 4, we know we can't grow and infect everybody.
Yeah.
So that was the zombie game. Did you listen to the I Love Rectangles game?
Not yet.
All right, so I'll let you listen to that. Did you listen to the Fibonacci game yet?
Isn't that we finish in the first lecture or the second lecture?
I don't think so. I don't think we talked about the Fibonacci game before.
Really?
We talked about Zeckendorf's theorem and Fibonacci numbers. Is that what you're thinking about?
Yeah.
Okay, so the Fibonacci game uses Zeckendorf's theorem to create a game. So why don't you watch the rest of the video?
Okay.
And then, that way, when you have questions, we'll then, we'll set up a time to meet again.
Okay.
And the goal is now we have, I think, a research topic.
Yeah.
Not involve calculus.
Yeah.
And I think it should be accessible based on the backgrounds of all the students in the group.
Right.
All right. So again, I think we have to do more of these smaller, one-on-one sessions as we try to find times that work for everybody.
So it's not, it's just an individual meeting.
Well, I would prefer not to do that. I think it's more effective if we can all be together. And frequently, if one of you has a question, almost surely somebody else has that question too.
Yeah.
But it's just, it's hard to find times. I'm going to say again to everybody, you've got to respond, within a day when I send an email, can we make a time work?
Okay.
All right, so I'll let you watch the rest of the videos, and then that will give you a sense of the possible research topic.
Okay.
All right, have a great day.
Yeah, you too.
All right,
Goodbye.
bye-bye.